Hello friends, I welcome you in lecture number 3 on residues. In earlier lecture we have seen how to find out residues using Lorentz series expansion of a given function at a given point. In this lecture we will discuss one more formula for calculating residue at poles without using Lorentz series. So first we discuss this result for that formulas, and then we will see how to apply these formulas to calculate residues of a function at poles. So this result says that an isolated singular point z0 of a function f is a pole of order m if and only if we can write our function in this form. If our function can be written in this form, f of z equal to some function of z divided by m power of z minus z0, where this function phi of z is required to be analytic at z0 and value of this function phi at point z0 must be non-zero. So if our function f of z can be written in this form, phi of z divided by z minus z0 to the power m, where this function is analytic at z0 and phi of z0 is non-zero, then we can say that function f has a pole of order m at z0. If m equal to 1, then we can say that function has a pole of order 1, that is function has a simple pole at z0. Pole of order 1 is known as simple pole. And if our function has a pole of order m at z0, then we have these two formulas for calculating value of residue at that point. So if m equal to 1, that is if f of z has a simple pole at z equal to z0, then residue is given by value of function phi at z0. So if fz can be written as phi of z over z minus z0 to the power 1, then f of z has a pole of order 1 at z0 and residue of f of z at z0 is nothing but value of this function phi at z0. Now if function has pole of order m greater than or equal to 2, then residue of f of z at z equal to z0 is given by m minus 1th derivative of function phi at z0 divided by m minus 1 factorial. So here we have to differentiate this function phi of z m minus 1 times with respect to z, and value of that m minus 1th derivative at point z0 divided by m minus 1 factorial will give us the residue of f of z at z equal to z0. So we consider one example to understand these formulas for residues, but these are very useful formulas. Here we are able to decide the residue of a function f of z at a given point without using its Lorentz series, so that will save our work. So here we are asked to determine the poles of the function f of z equal to z plus 1 over z square plus 9 and residue at each pole. So first we write down the given function f of z equal to z plus 1 divided by z square plus 9. So to decide the poles, we have to first check whether we can write our function f of z in this form or not, phi of z over z minus z0 raised to m. If we can write our function f of z in this form, where this function phi of z is analytic at z0 and phi of z0 is non-zero, then z0 is a pole of order m. So to write in this form, we can write z square plus 9 as z square minus 9. Again we can replace minus 1 by I square, so this we can rewrite as z square plus 9 into I square. This is z square plus 9, so we have to write in first we write in this way. Z square plus 9 can be rewritten as z square minus 9. So now we replace minus 1 by I square, so this we can rewrite as z square plus 1 z square minus, here minus 9 can be rewritten as 9 into I square, because I square is minus 1. Again we can rewrite this as square of z minus 9 can be written as 3 square, so we have z square minus 3I square. So now therefore f of z is z plus 1 divided by z minus 3I times z plus 3I. So this is rational function, and we know that this function is not analytic at these 2 points where function becomes 0. Here at z equal to 3I we have 0 in the denominator, and at z equal to minus 3I also denominator becomes 0. So this function is not analytic at z equal to 3I and z equal to minus 3I, and clearly these two are isolated singular points. So therefore f of z has two isolated singular points z equal to 3I and z equal to minus 3I, because this is rational function, and rational function has isolated singular points at those points at which denominator becomes 0. So now we have to decide the residue at each of these two isolated singular points. So for that first we check the behavior of function at z equal to 3I, and then we will discuss for z equal to minus 3I. So now at z equal to 3I, so we can rewrite our function as we keep z minus 3I in the denominator and we consider this portion in the numerator. We can rewrite f of z as z plus 1 over z plus 3I divided by z minus 3I. So here we write z plus 1 over z plus 3I divided by z minus 3I. So we can see now z minus 3I we keep as it is, and here we write phi of z, where phi of z is nothing but z plus 1 divided by z plus 3I. So now we have to check whether phi of z is analytic at z equal to 3I or not. So it is obviously analytic at z equal to 3I, because it is rational function and denominator is non-zero at z equal to 3I. So phi of z is analytic at z equal to 3I, and we have to check whether value of phi of z at z equal to 3I is non-zero or not. So we find out value of phi of z at z equal to 3I. So it is 3I plus 1, we put z equal to 3I here, divided by 3I plus 3I. So we simplify this, this is 3I plus 1 over 6I. Now we can replace 1 upon I by minus I. So we have 3i plus 1 into minus I divided by 6. So therefore value of phi function at 3i equal to we simplify this minus 3i square minus I. Here we multiply 3i plus 1 with minus I. So 3i into minus I minus 3i square minus I. Now if we put I square equal to minus 1, we have 3 minus I divided by 6, and this is clearly non-zero. So now we have written our function f of z in this form: phi of z over z minus 3i, where phi of z is analytic at z equal to 3i and value of phi at 3i is non-zero, and here power of z minus 3i is 1. So therefore we can say that z equal to 3i is a pole of order 1 of f of z. Okay, so therefore z equal to 3i is a pole of order 1 of function f of z, and residue of f of z at z equal to 3i is given by value of function phi at z equal to 3i, which we have obtained here. It is 3 minus I divided by 6. So we are using this first formula, that residue of f of z at z equal to z0 is given by value of function phi at z0 if m equal to 1. Now we have to decide the residue at another point z equal to minus 3i, and here so now we discuss at z equal to minus 3i. So for this point we have to write our function f of z in this form. We can write z plus 3i in the denominator, and now we write our function in this form. We require z plus 3i in the denominator, and we consider z plus 1 over z minus 3i in the numerator. So here we write z plus 1 over z minus 3i. So this is going to be phi of z divided by, and this I can rewrite as z minus 3i. So where what is phi of z? Phi of z is nothing but z plus 1 over z minus 3i. This is rational function. It is analytic everywhere except z equal to 3i. So it is clearly analytic at z equal to minus 3i, and value of phi at z equal to minus 3i, this is equal to minus 3i plus 1. We put z equal to minus 3i here, and here we have minus 3i minus 3i. So minus 3i is minus 6i, and we can replace 1 upon minus I by I, and here we put 6. 1 over I is minus I, so minus 1 over I is I. So therefore value of function phi at minus 3i, this is going to be minus 3i square plus I divided by 6, and if we put I square equal to minus 1, we have 3 plus I divided by 6, which is non-zero. So now our function f of z can be written as phi of z over z minus minus 3i, where phi of z is analytic at z equal to minus 3i and value of phi at minus 3i is non-zero, and here power of z minus minus 3i is 1. So therefore f of z has a pole of order 1 at z equal to minus 3i, also has a pole of order 1 at z equal to minus 3i, and residue of f of z at z equal to minus 3i, this is equal to value of phi at minus 3i equal to 3 plus I divided by 6, and so we are able to find out residue of f of z at z equal to minus 3i, which is 3 plus I over 6. So here given function has simple poles at z equal to plus or minus 3i, and we have calculated residue at each pole using that formula. So now we consider one more problem. Find the residue of f of z equal to z cube plus 2z over z minus I cube at z equal to I. So here given function f of z is z cube plus 2z divided by z minus I cube, and we are asked to find out residue at z equal to I. So we can see that our function is already in this form, phi of z over z minus I to the power 3. So we have to consider phi of z equal to z cube plus 2z, and this is polynomial function. It is analytic at each point in the complex plane, so it is analytic at z equal to I also, and value of function at z equal to I is I cube plus 2I. So this we can rewrite as I times I square plus 2. We take I common, so this is I times I square is minus 1 plus 2, so it is I. So therefore phi of I is non-zero. So f of z is written in the form phi of z over z minus I cube, where phi of z is analytic at z equal to I and value of function phi at I is non-zero, and because we have third power of z minus I here, f of z has a pole of order 3 at z equal to I. Therefore f of z has a pole of order 3 at z equal to I, and residue of f of z at z equal to I is given by value of second derivative of function phi at z equal to I divided by 3 minus 1 factorial. So that means value of function, value of second derivative of phi at point I divided by 2 factorial. So here we are using that formula that if function has a pole of order m at z equal to z0, then residue at z equal to z0 is given by m minus 1th derivative at z0 divided by m minus 1 factorial if m is starting from 2. So here we are using this formula for m equal to 3. So here we have 3 minus 1, that is second derivative at point I divided by 3 minus 1 factorial, that is 2 factorial. So we have to calculate derivatives of phi of z. So phi of z is z cube plus 2z. So now phi of z is z cube plus 2z. Therefore first derivative is 3 times z square plus 2, and therefore second derivative is 3 into 2z, that is 6z, and we are interested in the second derivative at point I. So we put z equal to I and we obtain second derivative at point I equal to 6i. So we substitute this second derivative. So therefore residue of f of z at z equal to I equal to, so we put in this phi double dash I divided by 2 factorial, that is 2. So here we have 6i divided by 2, that is 3 times I. So residue of f of z at z equal to I is 3i. Okay, so in this way we can easily calculate residue at a pole without using the Lorentz series expansion of a given function at that point. So here in this lecture we have seen how to decide residue at a pole and how to check whether function has a pole of order m at a given point. So if we are able to write f of z in this form, phi of z over z minus z0 raised to m, then we can say that if phi of z is analytic at z0 and value of phi at z0 is non-zero, then function f of z has a pole of order m at z0 and residue of f of z is given by this formula. Now this formula is not applicable for every function. For example, in earlier lecture we have seen this function z square times sine of 1 by z. So here we cannot write this function in this form, phi of z over z minus z0 raised to m. So for this type of function we have to use the Lorentz series expansion, and then we have to decide the coefficient of 1 over z minus z0. So this formula is helpful if our function can be written in this form. If we cannot write our function in this form, then we have to go by Lorentz series. There is some another formula also for residue of a function f of z at a pole that we will discuss in the upcoming lecture. So I hope you like this lecture. Thank you very much.